Oh, yeah, that's it. Thank you, Jen. Hello, everyone. Many thanks to the organizers for inviting me. It's a great pleasure to be here. So today, I want to talk about this problem in arithmetic geometry of likely intersections. So I'm going to start with a couple of simple definitions. So you take some ambient algebraic variety, smooth, and all varieties are going to be over the complex numbers. And you take two subvarieties. Then we say that the intersection is said to be, and here you can do likely, and that is if the dimension of V plus the dimension of W is at least the dimension of the ambient space, and it's unlikely otherwise. So dimension of V plus dimension of W, strictly less than the dimension of Z. Okay, so this is just a condition on dimensions. It's just an expectation condition. There is no assumption about the intersection being empty or not, okay? The kind of setup that I want to work in is a situation where these words of likely and unlikely have the meaning that they are trying to convey. So that the likely ones really are likely, and hopefully the unlikely ones are also unlikely. So the setup that I want to work in is a variety that has a little bit more personality to it than just an algebraic variety. Today we've seen several talks where people restrict to certain kinds of algebraic varieties because they have more properties than just a random algebraic variety. I want to do the same thing. The definition of what I'm calling having more personality is a little bit technical, so I'm going to skip it for a few minutes later. For now, let's just think about an abelian variety that works for us. So take A, an abelian variety, defined over some number field, over Q bar, let's say. So I would consider this variety has more personality because it's also a group. And the way that, or what happens when you have one of these varieties with more personality is that they now come endowed with a somewhat natural collection of subvarieties which are deemed to be special. So a special subvariety in this case is going to be, for example, if I said that this one has more personality because it's a group, then the sub-abelian varieties should also be considered to have more personality. So you would say, okay, special varieties are sub-abelian varieties. Okay, but also I will allow torsion cosets of sub-abelian varieties. So torsion cosets of sub-abelian varieties, these are also considered to be special. Now, why does it have to be torsion coset specifically? Why not just any coset? That's a very valid question. So this is just because there's going to be a more technical condition afterwards that makes sense why I want to restrict to things that are defined over Q bar, essentially. That's why I take the torsion cosets. But if you want to consider all cosets of sub-abelian varieties, then this is called a collection of weakly specials. Weakly special varieties. Okay, so there you go. This is in this case, my variety that has more personality. And here I've gone and I've chosen a collection of subvarieties and I've called them the special ones. Okay, so once you do something like this, then you can formulate what is called the silver-pink conjecture. So let me write it here. Silver-pink. So the silver-pink conjecture is going to try to say that the word unlikely is correctly chosen if you take an algebraic variety and you intersect it with a collection of specials. If you are only intersecting with special things, then the unlikely things really are unlikely. So for any variety V, I would want to phrase this. So you take a V, an algebraic variety, inside of your variety with personality, so inside A in this case. Then the intersections V with S special. Produce only finitely many maximal atypical components. Okay, so what does this mean? I want to say that if I take a random algebraic variety inside of A, and I intersect it with the special ones, then the unlikely intersections are not Zariski dense in V. That's what I would like to say. There is, of course, a caveat to that, because if V is itself special, then of course there will be one intersection which is all of V, and so it won't be, it will be Zariski dense inside of V in that case. So if V is itself special, okay, then you cannot say that the unlikely intersections are unlikely or that they don't generate all of V. So you have to allow for this to happen, and so the way that you do that is you say like, all right, take V, intersect with specials. There might be typical components, but there's only finitely many maximal things that show up. And what do I mean by atypical? Atypical simply means a measurement of how unlikely is one of these things. So an atypical component, I'll write it up here. An atypical component of V is a component of the intersection between V and a special one, such that I should call this a component, let's call this Y, such that the dimension of Y is strictly bigger than the dimension of V plus the dimension of S minus the dimension of the ambient space. So the atypical component is measuring just how unlikely is the unlikely intersection. If such an intersection exists, it shows you how unlikely is it. Okay, so this is the silver-pink conjecture. In the case of the abelian varieties, there are many other kinds of varieties that come naturally endowed with a collection of special varieties, like Shimura varieties, mixed Shimura varieties, and all kinds of things. This is a very important conjecture being studied heavily these days in Diophantine geometry and arithmetic geometry. It's very open. I mean, in none of the cases that are of interest, this conjecture has been proven. So it's a very, very difficult thing. It generalizes lots of very important questions, like conjectures about the presence of torsion points in varieties, like the Manin-Manford conjecture or Morel-Lang. In the case of Shimura varieties, it generalizes the André-Oort conjecture. It generalizes the theorems of faultings from the Mordell conjecture. Okay, so very important. People study it a lot. It's very open, but there's a lot of research being done, and lots of special cases have been proven. Now, the next thing. Yes, overall the possible special varieties. Correct, thanks. Yeah. Now, the next thing I want to observe is that the Silverpink conjecture, okay, it's trying to say that unlikely intersections are unlikely, but it doesn't really say anything about the likely ones, okay? So one can, if you like this conjecture and you try to prove it and you fail, maybe you will now try to do something with the likely ones instead, and you might say like, okay, I think I can formulate a likely intersections conjecture, like the Silverpink conjecture. And so maybe naively, you might come and say that, like likely intersections of the form V intersected with the special are Zariski dense in V. Okay, so this would be a naive statement to make. Okay, so here's the reason why this is naive, and you need to be a little bit more careful than just this. It is a good way of starting, but the one thing that can happen is that some algebraic morphisms respect special structure. For example, if you have a morphism, an isogeny of a billion varieties, then this takes specials to specials, okay? And if an intersection V with a special inside of A, if this is likely in A, this morphism could take this special variety and just collapse it to 0, for example, okay? And if that's the case, then the intersection here will not be a likely intersection once you look at the images inside of B. And if you believe the Silverpink conjecture, you would say in here, the unlikely intersections are not Zariski dense. This will become unlikely once you move on here, and so you should not expect likely density in that sense. So you need to be more careful about what happens with morphisms that respect special structure. Likely intersections could turn out to be unlikely under the images. So we need to fix this, and so that this is where the notion of persistently likely intersections. So we're going to say that V intersected with S is persistently likely, means that likelihood is preserved under, I'm going to say, special morphisms, by which I mean morphisms that respect the special structure. Okay, so the way that I would fix this statement now is that if the intersection between V and some special is persistently likely, then the likely intersections are Zariski dense. I'm just going to write it. Here. So let me add this. Jan asked me to use some colors, so I will. I'm going to put this in yellow. You know, to fix. Okay, so if the intersection with some special is persistently likely, then the likely intersections are Zariski dense. Okay, and this is the statement that Tom and I managed to prove. Okay, so now a little bit of history of this problem. So we're not the only ones who've studied the question of likely intersections. There's at least 4 different papers, all of which tackle this question in different circumstances, abelian varieties, Schumann varieties, mixed things, Hodge structures, whatever. All of us sort of like tackled the question during the pandemic because I guess we had nothing better to do. So we all approach the problem in different ways. These are different proofs with different levels of specificity. They all like, if you work in a more specific situation, you will obtain more specific results. And we'll get a lot more information in the problem you're working on. The setup that Tom and I are working on is a setup we try to be very general. So we axiomatize the whole situation as much as we could, so that it didn't really depend on anything. If you wanted to like get more general than whatever happened to be available at the time, then the method of the proof would still work. The method of the proof by itself is also different from the other proofs that are available in the literature. But furthermore, we were aiming for being very general, something that would not depend on like what was the kind of variety in vogue at the moment. Okay, so what is this situation? How does this work? Okay, so here I have to tell you a little bit of what does it mean to have this more personality. So the way this works is that the variety in question, which for example could be an abelian variety, if Z is supposed to be a variety with more personality, like an abelian variety, then the way that I witness the fact that it has more personality is that, okay, it comes from some complex domain. So this is here is a complex domain on which there is a group action, and it's in fact is the real points of the group. There's a group action on the complex domain. This group acts holomorphically and transitively. And then inside of that group, you happen to find what is called an arithmetic group, which is discrete. And then what all of this does is that it witnesses this variety as a quotient of D under the action of gamma. And then there is the quotient map pi. Okay. So an abelian variety is something that arises in this way. Like abelian varieties are built. Here you would have the exponential map of the abelian variety. And so you build it as a quotient of CG by some appropriate kind of lattice, correct? So this is the same thing in this case. And the group acting on, okay, the group that acts here is sort of itself, but seen as a real group, no? Seen like as R to G, acting by addition. Another example would be to take the upper half plane of complex numbers. There is a natural action by Möbius transformations of the group SL2R. And then inside of SL2R, you have SL2Z. And then the quotient of this by SL2Z is what is called sometimes as Y1, which happens to be isomorphic to the complex line. It's what you would call the coarse moduli space of elliptic curves. Okay. So, all right, on one hand, what I'm saying is that these varieties with more personality are quotient varieties. Okay, that's not by itself so exciting, but what the group action is doing is that it's telling you who are the special ones also. And the idea is that being special amounts to some extent to being bi-algebraic under this pi map. So really what happens is that the weakly specials is the same thing as being bi-algebraic with pi. So what this means is that in the domain, you can cut out a piece of the domain using just algebraic relations. There's the set. You can map it under pi, and you will get another algebraic set, cut out by algebraic relations. This map pi is transcendental, so pi doesn't usually send algebraic things to algebraic things. When it does, you will get something weakly special. And if those bi-algebraic things happen to be defined over number fields on both sides, then it is special. So this setup is the one that witnesses the special structure. And you can see that it's kind of technical, that it takes a while to like go through the definition of having more personality. Officially, yes, but in order for all of this to work out, you're going to require D to maybe have also some kind of Hermitian form in some cases, like in this case, a Hermitian symmetric domain. and other things like that. Like officially complex domain is just a complex domain, but for all of the setup to work, usually the domain will have to have more structure to it. But yeah. Yeah. Yes. Okay, so this is actually not necessarily required. So if you want to work like in Hodge theory, then the algebraicity of Z is not even true. Instead, what you have to do is you have to add here another piece of the puzzle, which is a map in this direction. This is an algebraic variety, and this is how you witness this algebraic variety has an admissible Hodge structure on it, and then this is the thing that witnesses that Hodge structure up here. And then this is not an algebraic variety anymore, it's just a compact manifold, complex compact manifold. But, okay, you have to assume some properties of this map F here, but the axiomatization that we gave with Tom allows for this as well. It's just that it's easier to think of when this Z is algebraic variety. Okay, so this is the problem of likely intersections. This is the setup that I work on. Now I need to tell you perhaps just a couple of words about what the proof looks like. So one common feature, I told you that we're not the only ones to work on likely intersections, and that we all sort of like worked on it more or less at the same time, and that we have different proofs that are very different in flavor. But one common feature of all of the proofs is something about functional transcendence. And it's this thing called the Axe-Channel theorem, if you've ever heard about it. So the point is that, well, okay, there is this map here which is transcendental, no? And you really need to understand what kinds of algebraic relations this map likes. And Axe-Channel is the kind of theorem that will tell you what are the relations that it likes. And fortunately, at this point, we have Axe-Channel theorems in a wide variety of functions. Certainly, all kinds of exponential maps, this is known. For the J function that shows up here, this is also known. For automorphic functions, this is known. We have Axe-Channel theorems in lots and lots of cases. Sure. So the simplest version would be for like the complex exponential function. Okay, and it goes something like this. Take a variety inside of C to the n times C star to the n. This is an algebraic variety. And then consider the graph of exponentiation, by which I mean simply just this, no? Like the n-fold graph of exponentiation. Take a component of the intersection between V and the graph. This is an analytic component. Then the dimension of the component is going to be the dimension of V minus n unless there is a good reason for this, which is the unless part is what are exactly the relations that the exponential map likes. And in this case, in the case of the exponential map, so the projection, the first projection, okay, so this has two projections, one to the linear side, one to the multiplicative side. The projection of U to the linear side is contained in a translate of a Q-linear subspace of C to the n. So what this is saying is that the only things that exponentiation really understands are Q-linear relations and their cosets. And the images of things like this will give you subtori and cosets of subtori, all possible cosets. Okay, so this would be an axiom for just the usual exponential function, and then similarly, this axioms for all of these other maps. Okay, so now maybe maybe one or two words about what the proof is going to try to do. So the way that we decided to tackle the problem was to count dimensions. Now, yeah, I decided to use, but I erased it. Okay, so the statement about likely intersections said that if you have something which is persistently likely, then the likely intersections will be Zariski dense. You can do better. You can get Euclidean dense. So the way that we do this is, okay, take an open subset of V, and by open I now mean Euclidean open, because I can show that it's actually Euclidean dense. Now, having a special variety, like we said, being special comes from the fact that it's bialgebraic with respect to this map pi. But the only way, so this is something that needs to be proven, the only way that you can, something like that could even arise is if you happen to have sort of like let's say, a subvariety with personality. So there needs to be a subdomain contained in here with the action of a subgroup of G, okay? So that the restriction of gamma 2H gives me a quotient here, D prime modulo gamma sub H, which has a map there, and the image in here is the special guy. This is the only way that special things arise, is by taking sort of like a subdatum of all of this setup. That's the only way these things show up. So if you are assuming that V intersected with S0 is persistently likely, then this special variety must come from some datum upstairs. So you go and you choose your datum, so that, okay, pi of D prime is going to be S0, so this is the special person. This is the Euclidean open subset of V. And now you consider a specific set, which is nothing more than the pairs of elements inside of U times G, so that U is in pi of a translate of D prime. Okay? And I would like to compute the dimension of this set. And the way that I would like to do this is by considering the projections to U and to G, GR, and using the fact that both of these maps are surjective, I would like to compute the dimension of R. So if this works, let's say, before I tell you how that works, if that works, what's going to happen is that you will be able to show that the dimension of G is the same as the dimension of the following set, a smaller subset of G, which is the elements in G of R, such that U intersected with pi of G of D prime is non-empty. This happens to be enough because if these two dimensions are the same, then, okay, I'm skipping ahead. I want to compute the dimension of R, and I will do it by computing the dimensions of the projections and then the dimensions of the fibers, and I will make sure that because they have to be the same, this will allow me to conclude this in the end. and the fact that these two things are equal then will imply that this set has non-empty interior. And then the fact that G of Q is Euclidean dense in G of R implies that this set must have rational elements, and the rational elements are the ones that produce more special things. If I have one special guy, the rational translates are also special. And that's the end of the story. Then you've produced an element in U, an intersection in U, and you got the special guy. So in the last minute probably that I have, oh no, I have like 5 minutes. Okay, so let me just say one word about what's going on in the background. The word that I want to say is this one, O-minimality. Okay, so O-minimality is a way of doing analysis, real analysis, and also complex analysis, but you restrict yourself to only nice functions. Okay, so there's none of the functions that show up in the book of counterexamples of analysis, none of those show up. Everything that you can build in O-minimality is a finite union of smooth manifolds. In particular, everything has a well-defined notion of dimension, and the fiber dimension theorem holds. So these kinds of things, computing the dimension of R by looking at projections makes sense, and you can do it. And the fact that two sets have the same dimension implies, in particular in this case, that this set has an empty interior also. So if you've never studied O-minimality, I don't know. If you need analysis at some point in your life, but you like geometry, then I strongly recommend studying O-minimality. It's a very useful technique to just remove all of the noise of analysis and stick with the nice parts without losing the information. Yes, so there is a book which is intended for like, I would say, I don't know, let's say, for mathematicians which are not logicians, is Lau van den Dries has a book. It's called Tame Geometry. O-minimality is also a technique that has allowed us to prove these kinds of results. These kinds of results have been proven also using differential algebra, but for a while, many of the functions that we needed to study did not have a differential algebraic proof. And the first proofs that were proven were using O-minimality. Similarly, the cases of silver-pink that have been solved thanks to O-minimality and also point counting techniques. So yeah, I can only recommend it. It's very good. So that takes care very, very informally of how more or less the proof goes. I take this set, I compute the dimension, I show that these two dimensions are equal, and then using O-minimality, that implies that this thing has no empty interior, and then using this density, I get an intersection point inside of U, and because U was arbitrary, bam, Euclidean density. Not only that, but in fact, you've managed to show something a little bit stronger, which is not just when you look at all intersections of V with S, you get Euclidean density. It is enough to restrict yourself to the translates of D prime. You don't need all the specials. You just need the translates of S0. To look at translates of S0. And by translates, I mean a rational translate of D prime and then apply pi. And then that gives you Euclidean density. Okay, so I guess what remains is to say maybe a word or two about this. All of this assumes that you use persistent likeliness. So persistent likeliness is going to show up when you compute the dimension of R using this projection here, because, well, then you will have to do something about, when you start computing this dimension, you will notice that either the dimension is what you want or it's an unlikely intersection. And if it's an unlikely intersection, then you might be thinking like, oh no, I'm sort of like stuck in an infinite loop, but no. Axe channel gives you a way of handling the unlikely fibers that come here. And you can like reduce dimension and then sort of like induct down and prove the statement. So that's good. That's how it shows up. But now the question is, how easy is it to check this thing? Seems like maybe, in principle, at least, it seems like you would need to check like infinitely many morphisms of things. Okay. All right. So in principle, yes. But in many cases that we care about, checking persistent likeliness is not so bad. I erased the examples. So one example that I mentioned was the J function, right? In the case of the J function, it's actually very straightforward to compute, to check whether something is persistently likely or not, because you only need to check finitely many morphisms. And this is again something that you're able to know this simply because of the whole general setup, the fact that there is a group acting on the domain and so on. The only way that a group acting on the quotient down here has a morphism to some other domain with a quotient and so on. That this respects special structure is that this map has to be induced by a morphism between the groups that induces a morphism at this level and then a morphism at this level. So you just need to look upstairs at the level of the groups. And in the case of SL2R, or if you're looking at the upper half plane like to the n, so that you get here y1 to the power n, here you have SL2R to the n. And so the only groups that are going to show up because of the simplicity of SL2R is that you only need to consider projections of y1. So if you have a subvariety inside of y1 to the n, and you have a special guy, and you want to know whether this intersection is special, is persistently likely, all you need to do is look at this intersection under just the coordinate projections to y1 to the L for all L. There's finitely many of those, and you can check, at least for small numbers, you can check by hand. So yeah, it's manageable in cases that we actually care about to check this condition of persistent likeliness. Okay, so how am I doing on time? Okay, yeah, I think that this should stop here. Yeah, thank you very much. Definitely there's a p-adic version of all of this. From the silver-pink point of view, the statement is just about algebraic variety, so we don't care about the topology. But the condition about Euclidean density could be switched for p-adic density, absolutely. That makes sense. The thing that is stopping you is the X-channel result. You would need to prove an X-channel theorem for the p-adic exponential function or the p-adic J function and so on. In principle, there is no reason why that shouldn't be true. It's just hard. So yeah, it could work, but you need to. Yeah. Yes, right? When the intersection is likely, then generically the intersection should be transversal. The X-channel theorem, which I also erased unfortunately, in fact shows that when you intersect the variety V with the graph of exponentiation, it is, except for some proper Zariski closed subset, it is going to be transversal, a transversal intersection throughout. So yes, there might be accidents, but generally, yes, generically transversal.